So I mentioned when we started going over valence bond theory that the examples that you could really possibly come across, even on the final exam, if it was the ACS final, are going to be a lot simpler to deal with than all of the kind of details that I just explained to you. And it really kind of all boils down to that one short chart at the end. So for this, I've pulled an example out of the end of chapter 8 in your book. This asks you to describe the hybridization of each carbon atom in this molecule, propyne C3H4, which they've given us the Lewis structure for this already. And we're not going to make a rough sketch of the molecule showing its hybrid orbitals, but what we are going to do is count the number of sigma bonds and pi bonds, because that is a common type of question that you might come across. So when it comes to classifying the hybridization of any atom that is hybridized, all we really need to do is count up the charge clouds. So, for instance, if we look at our first carbon right here, this has two charge clouds, one here and another one here. Remember, in terms of counting charge clouds, we don't care if we have double or triple bonds, we just count the number of separate atoms. And there's no lone pairs here, so it's just those two charge clouds. So, since this thing has two charge clouds, this is going to be sp hybridized, if you remember from the previous chart. So that's our hybridization for that carbon. Let's look at the next carbon over, this one right here. And just like the previous carbon, this one also has two charge clouds. The one carbon over here that it's bonded to, and the second carbon over here that it's bonded to. So this will also be just sp hybridized. Pretty straightforward. And our third carbon, which is right here, I'll do this one in green. This is attached to 1, 2, 3, 4 different atoms. Again, it has no lone pairs. Carbon often doesn't have any lone pairs in most molecules, really. Since this is attached to not 2 but 4 atoms, that's the number of hybrid orbitals that we need to account for. So this is going to be sp3 hybridized. So that comes from the hybridization of an s orbital and 3 p orbitals for a total of 4 orbitals for the 4 different atoms that we need to connect it to. So we have hybridizations of sp, sp, and sp3. Now, I told you we weren't going to worry about sketching the molecule. Because that's going to be a disaster if I try to do it with the mouse, but also, even if we were doing this on the board, that's not a question that you'd see on an exam, either one of my exams or the ACS final. So what we can do instead is count up all of the sigma and pi bonds. So let me go ahead and erase everything, and we'll go into these bonds and show how many sigma and pi bonds there are. Remember, the easiest way to deal with this is just to count the number of bonds for the number of sigma bonds, because each bond will have exactly one sigma bond. So this bond right here has one sigma bond. We'll come back to the triple bond later, and all of these single bonds here likewise are going to have one direct orbital overlap for one sigma bond. And that's true for each of them. Finally, we'll come back to this triple bond right here. So if you think back to a couple of slides, you might remember that we have two sp orbitals, one from each carbon, directly overlapping each other. So that's going to be one sigma bond, and then we have the remaining two bonds formed from indirect overlap of unhybridized p orbitals, 2 on each carbon. So this has 2 pi bonds. And so if we had to count up the total number of sigma and pi bonds, then we'd have one sigma bond there on the left, one sigma bond between the two carbons, and then 4 sigma bonds around that carbon on the right, for a total of 6 sigma bonds. And our only pi bonds are in that triple bond, so we'd have 2 pi bonds.